Hello guys, today we're going to look at Markov Chains 4.9. It's actually a pretty interesting topic, a pretty interesting subject. And it allows you to figure out figure out what's going to happen in the future or predict what's going to happen in the future. And we can obviously see a bunch of examples of when and why we would want to use this. And it might just be the way that this is the math that's in the background when you're trying to make predictive models. And we all are going through times where we got to figure out, well, if we do this, then what will happen? If we do that, then what will happen? So if we know the probability of a given state, predicting just by knowing the current state of the system and what happened before, then the process of change is called a Markov chain or a Markov process. That is just kind of what it is at that point. So, and we have to kind of you think about it like a chain of events, basically. So Markov chain has k possible states, and we're going to just look at a couple of possible states, not make it too complicated. You would probably use computer models to figure out more complicated states. Then the probability, and we're talking about probability here, and I want you to keep that in mind today. So probabilities have to add up to 100%, and we'll make a connection what we had done before, I think even in chapter 1, when we have, so in the system state that I at any observation, state of J in the preceding observation, we have all this stuff, and we're going to make up a transition matrix. And what we had called before was a migration matrix. And it's kind of the same thing we're going to look at again today, but this migration matrices and what impact is that migration matrix going to have on a population or a certain thing. For example, in the three-state matrix, we have three possibilities, and all of these probabilities in each of these columns, again, from the past, they're going to add up to 100%, and I want you to keep that in mind. So that column has to add up to 100%. This column is going to be three different values. That's also going to add up to 100%. And the last column is going to add up to 100%. And what we're going to be dealing with, they're all going to add up to 100%. So keep that in mind. We're not going to, I like to read these columns vertically, or the matrices vertically, to make sure that we have, if we set it up right, then we have 100%. So the state vector for an observation of a Markov chain with k states is a column vector whose ith component is a probability of the system at that ith state at that time. Now, what does that mean? Let's look at an example, and that'll probably be the best way to observe this. So we have an example, and this is already in like a tabular format, and make sure we know how to read our matrices. That's just as important as making them up. So we have this certain company called Rent-A-Lemon, 3 locations, and they have airport, downtown, and the valley. So what's going to happen to this company, and if they wanted to decide like how many cars they need at each of these 3 locations, the airport, the downtown, and the valley. It's just 3, call them location 1, location 2, and location 3. It really doesn't matter. And notice that again, these columns add up to 100%. And so I'm going to look at that first column and what that says, and making sure we know how to read this. It's saying that 95% of the people who rent their car from the airport are going to return it to the airport. And then if 3% of them who rent it from the airport are going to return it downtown. So that's what that one is kind of representing. And then 2% of the people who rent it from the airport are going to return it to the valley or to location 3. And so that's a rental car company example. You might have, I'm going to go old school on you, but maybe something that you can relate to is you can rent or loan a book from a library and return it to whatever library you want to. So if you 95% of the people who, in that using that same example, 95% of the people who rent it or borrow their book from the Chantilly Library, we're going to return to Chantilly Library. But if you are close to the Centerville Library, you can return to the Centerville Library or the Fairfax Library. And then obviously the highest probability in this case is going to be if you rent it from location or borrow it from location one, you're going to return it to location one. And that's why we have the highest percentages at each of these three locations. So 90% of the people who rent it from downtown return to downtown. And we're going to use these probabilities 100%. Make sure you write that as a decimal. So that adds up to 1 or obviously 100%, 1.0, 0.9, 0.02, and 0.08, 0.005, 0.005, and 0.9 adds up to 100%, right? That is your quick fifth grade math review on percentages and writing them as decimals. And then if we write that into a matrix, then obviously it's going to be the same thing. We just don't all the time have the labels on that one. So that one was the airport, that was downtown, and that was the valley. And this is our from to matrix. I'm going to call it a from to matrix. Probability in each column add up to 1 or 1. We got to keep it 100. So the matrix with this property is called a stochastic matrix. Not all matrices obviously are going to be this nice and neat. And it's going to possibly change in the future as you change your behaviors. But let's assume that the behaviors don't change. And then we have what this initial state means is that initially, like at the grand opening, and they have all three locations opening up at the same time, or maybe this new valley location opened up, and they have, let's just say 200 cars in their fleet. Just making that up. So what this means is that 50% of the cars are at location 1 or at the airport. So obviously 100 cars would be there. And then 60 cars are at the downtown location, and then 40 cars are at the valley location. And that could be, so that is just an example in what those numbers mean if you have a 200 car fleet for that one, okay? So what's going to happen as you open up the new store, and what percentage of the cars are going to end up, if the policy is they can return it wherever they want to, or maybe you would charge more if you don't return it to the same place you rented it from. Well, what happens is after year 1, and we've done this before, like with state population negating births and deaths is what the homework problem looked like and the test problem looked like. So what happened is you just throw this stuff into the calculator, and now we have a little less than 50% are now at the airport, and a little less than 30% are at the downtown location, and then a little more is going to be at the valley location or location number 3. So in general, going back to calculus a little bit, we have a k+1, or actually you probably saw that in algebra 2 at k+1 recursive formula. So what is the next state? Well, it depends on the prior state. So this is like the next year, the next day, and then that depends upon the migration matrix for k = 0, 1, 2, and it goes on forever and ever and ever. So that's what's going to happen. And so you would have to crank that out. And eventually, will this thing ever change? Well, I mean, will it always change? And if you have this basic thing, as long as this matrix right here does not change, then eventually we're going to reach what we call a steady state. So again, those two numbers kept going down, and this percentage at the bottom went up. So, and then will they continue to go down and up forever and ever? So if we just said, all right, that's going to continue to go down, that's going to continue to go up, then eventually, if you didn't know any better, then you would say that we're going to have 100% of the cars are going to end up at that new location, that valley location, right? Same thing with books. How are you going to distribute those out? So, and then we keep going and keep going to see that this keeps going down. The top two numbers keep going down and the bottom numbers keep going up. So that eventually went from, we'll just call that 47% to 42%. But now we can see, and I don't know exactly when, you can answer that question later. Maybe it would probably use the only thing I can think of is you would use a computer model to find out when it actually happened. When was there no change? So this is what happened for this is day 49, which is call it days, why not? Day 49, we have 42%, 28%, and 30 or 31%. I don't know if those numbers added up to 100%, but then you can see that there was no change. So we're saying that day 49, that percentage is the same as day 50. And now we have whatever those percentages were. And obviously, you would take out, if we still had a 200 car fleet after 50 days, then you could find out how many cars ended up at the airport. And those, each row represents the same thing. That's the airport, that's still downtown, and that's still Valley. And so you would have to, if all you had was your calculator or a pencil and paper, you could crank it out. Is there a better way? I'm going to spoil the answer for you and say, yes, there is a better way of doing that. And that vector is called the steady state vector. So we found the steady state vector. We didn't know when it reached the steady state. We just know that 49 was the same as 50. And it also looked like 48 was the same. I don't know if 48 was the same as 49, but I do know that 49 is the same as 50. So there could have been a slight change between 48 and 49, but we didn't look at that. So we have what we call a steady state. So how do we build that? By reviewing, let's say that this is actually, I did a little bit of research online. And this is actually a great system right here. Actually, this college is pretty good. 80% of the current alumni who contribute 1 year is also going to contribute the next. And 30% of those who did not contribute the last year will contribute the next year. So, and now we want to construct the transition matrix and an initial state. So that information is not given to you. So I'm going to make that up. And this is the making up part that I had to figure out, like what is plausible right here. So this one is not given, but we can get the transition matrix from that one. So you might want to pause the video right now and see if you can come up with the transition matrix that represents that. Keeping in mind that the columns have to add up to 100%. And what will that migration or transition matrix look like? Continue till you find the steady state vector. And so now once you have that, you're gonna see if your answer checks with mine. So this is the migration matrix that I already set up. And again, what this is saying is that 80% so I have a last year and I have this year. So looking at the data, and what does that data tell us? This is again telling me that 80% of the people who contributed last year also contributed this year. So that implies that 20% did not. And again, we have 100%. I'm not even gonna write that down because you're smart enough to know what that means. And now I have 30% of the people who did not contribute last year did contribute this year. That means that 70% of the people who did not contribute last year continue to not contribute again this year. And let's assume that that does not change. So we're going to have, and it's going to continue on forever and ever and ever. And we know that things change, and the reasons that a certain population would or would not continue to contribute to an organization like the colleges, their school. So let's assume that we have a the initial state, let's just call it 2018, whatever. And this is saying right here that 30% of the people, 30% of the alumni actually do contribute to their school, and 70% do not. And that might be for UVA. I'd kind of search for UVA or another school, and I know that the top 12 schools, it's like they're hovering around 40%. So I just reduced that a little bit and called it, just called it 30%. I think the one local school that I did find, it was like number 12 was Washington and Lee, and they're like around 41%. But like, so your Ivy Leagues obviously are going to be in the high, that's where all the schools were. So, and then, so this would be for 2018. So what happens is when you multiply this matrix, we'll call this one X naught. This is what happens when I do the migration matrix, or the times X naught, or 2018, and I get this 2019. And I was kind of surprised when I put that in the calculator. I said, hold up. And I then also used another simple process for that, just to check it. Did those numbers make sense? Well, now we're up to 45% actually did contribute, and 55% did not contribute. Oh, and I said, all right, well, let's see if that makes sense. So let's say we have, I just changed it to real people-ish. Let's just say I have a small organization, a small alumni base that we're looking at, and I just did 100, right? So what that is saying is that 30 people did contribute and 70 people did not. So I take 80% of that 30. And then, but since we had the 30% of the new people, and I think that's a very high percentage, they did not contribute last year, but they're going to contribute this year, and multiply that by 70, you get 45. And then similarly, you would get the same thing for getting the 55%. I actually didn't do that math, but I'll let you do that if you would like to. So now what's going to happen? So what will happen is we're going to reach a steady state where that actually 75% of the alumni will contribute and 25% of the alumni will not contribute. And there is a way, and it's actually on the next slide, of how I did that so quickly, so I don't have to run 50 iterations of this, because I don't want to do that. We're going to come back to how I got that 25 and 75%, and 75% did. So there is a process that it's called in the long run, the migration matrix times X is going to stay the same, and it would be N, and they actually use K plus 1. So then the now year, it's what I refer to it, is going to be the same thing as the next year. Okay, when it didn't change, this vector right here. So in our case that I had 75 and 25%. So multiplying both sides by the identity matrix doesn't change it anything. That's one way we can do that. So we want to figure out, well, this is what we're trying to find right here. We're trying to find out, what is this steady state? So we can do some simple arithmetic, and we can just move this I times X over to the other side. And then we can factor out that steady state vector, and that equals 0. So M minus I, and that is very simple math to do. Take that migration matrix, and for a 2 by 2, we are just going to, subtract the identity matrix, which is 1, 0, 0, 1. And that's, again, pretty easy to do. And that's how I did that. So let's go back and let's see what math I did on that one. So M minus I would be negative 0.2. This is M minus I. And then 0.3 doesn't change. 0.2, and then negative 0.3. And I want to set that equal to 0, so I'm going to augment that. And I'll let you guess how we're going to solve that matrix. And then we'll talk about ways that will be done. So, all right, so I had to press pause for a while, and I'm sorry for that, those technical difficulties that I had. But So we're going to factor that out. We're going to solve that equation, and we're going to find the steady state. So to find that steady state vector, basically what we're going to do is we're going to do n minus I times x. We just want to figure out what that is. That's a question mark right there. And we're going to set that equal to 0. And we're going to do the exact same thing that we have done before. So n minus I gives us negative 0.19. Then we get a positive 0.19. Now, once I do, again, from at the very beginning, each of those columns add up to 100%. But once I am changing it, n minus I no longer equals 100%. Just want to state that. And then that's going to be negative 0.26. So basically, these things are, the columns are going to match each other, kind of always. And then I want to make this equal to my steady state vector. When does that equal 0? So we would augment and row reduce this, and you're going to take out your calculator, and you're going to actually just put it in there one more time, what I want you to punch into the calculator. And then you're going to have an answer. And then we'll talk about how to make that into a steady state vector. And this is going to be kind of parametrically. We don't know what this stuff represents, but when I do this and then the row reduction, and once I hit math frac on this one, we get 1, and we get negative 26 over 19. And we have 0, 0, 0, and then you don't really need that, but we should know how to interpret that. And what this means is that x1 equals 26 over 19 times x2. And again, x1 and x2. Let me change colors on this one. And now we have that x2 equals x2. So now how can I get my steady state? Remember, our steady state has to add up to 100%. And we don't have 100% right here. We have more than 100%. So when I say that this is my steady state, I can factor out that x2, and we get 26 over 19, and then we get 1. So that's what x1 and x2 represent. So it'd be x1 and x2, right? And now we can see that this thing says that x1 equals 26 over 19 times x2, and x2 equals x2. But remember, that has to add up to 1, and it doesn't. And I am kind of slow, and so there is a process, and you might be able to think about the process differently than I can. But what I do is I just say, well, I'm going to change kind of the magnitude of that vector. And if I change the magnitude of that vector, or make a parallel vector, or however you want to think about it, then this is basically the same thing as if I multiply that by 19, change the length of it. Ooh, but that still doesn't add up to 1. But if you add those up, that adds up to 45. So it's just like a ratio. So we have 26 over 45, and we have 19 over 45. And those two fractions, boom, add up to 1. So that will be my steady state for that vector. Okay? So that's how you do it. That's the first one. Looking at example number 2, you're going to find that steady state, and you probably want to do that, press pause on it, or you kind of look at the notes. It's fine too, as long as you understand how to do it. I'm fine with that. So if I subtract I from it, so this is my migration matrix, m minus I, put that in parentheses, because I don't feel like writing it again because I'm lazy, equals 0. So m minus I is going to give you negative 2/3. And you kind of know that the only thing that's going to change are those values along the diagonal. Hopefully that doesn't surprise you. And all the other ones I'm just going to copy. So 1/3 and 1/4 and 1/3 and 1/2. So this is going to be my m minus I. And I know I'm going to have to solve this thing, so I'm going to go ahead and augment that with the 0 vector. Just going to change the color just because. And then you're going to row reduce that. And when you row reduce it, what you get out is you get this vector right here. This matrix right here, 1, 0, negative 1/4. And I think if you're looking at the notes, then I actually didn't augment it. You can, if you would like, just so you can see what we have. And we're always going to have kind of a free variable in this one. Okay, and again, that represents x1, x2, x3, and those can be whatever. And again, going back to that one, that's going to be our airport, downtown, and valley. So we can find our steady state for that one. And I'll go ahead and just slip in a row of zeros so you can see that still equals 0. And so what this says, and because I am slow, I have to write it out. And I say that, well, what this says is that x1 is going to be 1/4 of x3. And x2 is 1/3 of x3. And x3 is 1 x3. And you obviously don't need that 1. And so there it is. That's what it is, but it's not in parametric form because really all we have to do is factor out our x3s, right? Factor out that vector. And now we have, what did I want to do? Hit this button, then I can extend the page. And so now, go back to my pen, talking out loud. Now we have our steady state vector. X is equal to 1/4, 1/3, and 1. Ooh, but again, remember that they have to add up to 100%. We want our probability vector. That's not 100%. And you obviously know that. So how are we going to do that one? Well, we're going to multiply everything by 12. And that's how I get those numbers. So we have 3, 4, and 12. And then again, it's all about ratios. So if you look online, and I just randomly made, just to be playing around with Blackboard, the college poster that you can do, I made that 12. Oh, that ends up 19. My math was off a little bit. I said that was a 10,000 point assignment. Well, that's fine as long as I keep my ratios the same. Then I can have a class where each test is worth 10,000 points and each homework is worth 500 points. So it's all about ratios and understanding that those are basically the same thing. So, and that is my steady state, and I'm going to check that equals 100%. Remember, keep it 100. And that is basically it for finding a steady state vector. Let's just look at one more example on that one. So suppose that 3% of the population of the United States lives in the state of Washington. Suppose the migration matrix of the population in and out of the Washington state be constant for many years according to migration probabilities. What percentage will eventually live if currently we have 3%? So, that's our initial state. So initially, we'll call that thing X naught. We have 0.03% in the state of Washington, and 97% is not, right? So what percentage, but we have to have a migration matrix. Now that is basically given to us, okay? So in that first example with the colleges, I gave you the migration matrix and what you weren't given the initial state. So we would kind of do that same thing, M minus I. So you don't even need that 3%, but I can tell you what the steady state is, and you can find out, well, when it's going to be. You can tell me the percentage of the population at year 10, and is that a steady state? Well, I don't know. When does that equal 0? M minus I, or M times X equals X. That's really the same thing, right? So M minus I is going to be negative 0.1. That's going to be positive 0.1. 0.01 doesn't change, but that's going to be negative 0.01. So the columns are going to be the same absolute value. So we're going to see that when we row reduce that one with the zeros or without the zeros, you would see that you have 1, negative 0.1, 0, and 0, right? And this is one where you could have done it probably without a calculator. So what does that mean? Well, that means that x1 is equal to 1/10 of x2, and x2 is free. Okay, so and what did x1 represent? Well, x1 was Washington, and x2 was everyone else, which is use the word else in there. So is our steady state 1/10 and 1? Obviously not. So again, we're saying that we have to have a ratio of 1/10. In order to do that, just going back to fractions, we have to have 11 parts, and 1 out of 11, and then we're going to have 10 out of 11. And now I can see that, and kind of I'll just do this little side, do that same algorithm multiplied by 10. Whoops, that gives me a 1, so that 0 is not there. And that's going to give you 10, so you actually have 11 pieces. 1 out of 11 is going to live in Washington, and 10 out of 11 is not. What is 1 out of 11? Well, now we're saying that 9.09%. So the population of Washington is going to triple, more than triple. Ooh, can they handle it? Let's, I think you kind of know the answer to that one. So that is, that's all that we have for the examples in 4.9. Thank you.